Here we have notes for chapter 9.7 on Taylor polynomials and approximations. So first off, polynomial functions are very useful. It can be used to approximate other transcendental functions such as sine of x, exponential function e to the x, and natural log of x. Polynomial functions are very versatile, and it's easy. These are functions that are easy to manipulate and easy to use. And we can use these functions to help us create very similar copies and sometimes even exact copies of these other types of functions. So first example says find the equation of the tangent line for our function sine of x at x equals 0, then use it to approximate sine of 0.2. Is this an over or an under approximation of the value at sine of 0.2? Well, first, we do know how to use a linear approximation. We simply create a tangent line where the slope matches the point on the curve. So if we create the tangent line to a curve at a point, then we can get a pretty good approximation of the function of the curve as long as we are choosing values that are close to the point of tangency. So here the tangent line equation is basically coming from the point slope form for a tangent line. Y minus y sub 1 is equal to slope times x minus x sub 1, or f prime of c. So if we want to create a tangent line for this specific function at 0, we can do that, right? So first off, the order pair at 0 for our graph, that point of tangency will be at 0, 0. So if I plug 0 into sine of x, I'll also get 0. And to find my slope, I can find the derivative. So the derivative of f of x, of sine of x, will be cosine of x. And then if we want to evaluate the derivative at 0, f prime of 0 is equal to cosine of 0, which is 1. So our slope is 0. So f prime. Our slope at 0 is 1. Our order pair is at 0, 0. So when we plug into our point slope form for tangent line, for our tangent line equation, we have y minus 0 equals 1 times x minus 0, which is essentially y equals x. So if we graph that line and our curve y equals sine of x, then we get something that resembles this graph there. And just to test what type of values that we would get, if we plug in 0 into our sine graph, we're going to get 0. If we plug 0 into the tangent line, we're also going to get 0. So at the center, at the point of tangency, these graphs, the curve and the tangent line, will always share that same value. But as we move a little bit further out, for instance, if I plug 0.2 into sine graph, I'll get 0.198. And if I plug 0.2 into the linear function, I'll get 0.2, which is pretty close. But the reason why it's pretty close is because we're choosing a value that is very near the point of tangency. But as we veer further and further out from the center, then our approximation will get less and less accurate. And as we can see, the tangent line will produce a y value of 0.2. Our sine curve will produce a value of 0.198. So therefore, our tangent line will produce an over approximation of the curve sine of 0.2. Now, if we think about a tangent line, obviously, this is not a great model for our sine curve. Sine curve obviously has curves, and the line with the straight line, there's only so much you can do to match the actual curvature of this graph. However, if we increase the degree of our polynomial, of our approximating function, then we'll have a better chance of having that function wrap itself around the curve and make a better estimation. Okay. So the equation of our tangent line that we just saw is called the first degree Taylor polynomial. Taylor polynomials of higher degrees can be used to obtain increasingly better approximations of non-polynomial functions, such as sine curve, exponential e to the x curve, natural log of x function, within a certain radius from a center of approximation x equals c. So looking at example 2, on our calculator, if we graph our sine graph and put that information within a certain window in our graphing calculator, and then in y sub 2, we're going to successfully add more terms each time, and we're going to increase the degree. So in this case, let's say we're using a polynomial of 7th degree of this function. And if we were to plug sine of x and this polynomial in, we can see that our polynomial will do a much better job of matching the graph of our sine curve. So in our calculator, we plug in sine of x for y sub 1. For y sub 2, we can plug in this polynomial function. And if we hit graph after we adjust our window setting, so here we have our sine curve. And then here we have our polynomial of degree 7. And we see that it's going to do a pretty good job of matching our sine curve within this distance, this distance away from 0. And if we follow this pattern, and if we keep increasing the degrees, then our curve will wrap itself better and better around, our graph, our polynomial will wrap itself better and better around this sine curve here. So the more terms that we add, and the further that we can get that polynomial to wrap itself around the curve over a larger radius, over a larger interval. And if we were to test some of the values centered, first off, the center is at 0, so therefore our sine curve and our polynomial will have the exact same value. And even if we plug in 0.2, we're not able to see much distinction between the y values. But as we go further and further out at pi over 2, it still does a pretty good approximation, but we can see that as we get further and further away with this 7th degree polynomial, it will only produce a pretty good approximation depending on how far out we go. Okay, so Taylor polynomial, simply a polynomial that will approximate these other types of functions and these other functions values in a region that is relatively nearby the center. And right now our center is 0, but we're going to talk about how we can adjust that and create and have this polynomial start at a different center on the matching the graph. And our tangent line equation is basically a 1st degree Taylor polynomial. And the second graph that we function that we graphed was a 7th degree Taylor polynomial. As we can see, a 7th degree polynomial will have a better shot at matching the curvature of our sine graph. Okay. All right, let's look at the next page here. So moving on to definition of an nth degree Taylor polynomial. So if our function has n derivatives at x equals c, and c is our center of approximation, then this polynomial, we can call this p sub n of x, and n just represents that this is the nth degree Taylor polynomial. So we saw that the linear function was a 1st degree polynomial, and the last curve that we put into our graph, into our graphing calculator, was a 7th degree Taylor polynomial. But now if we have an nth degree Taylor polynomial, then it's going to follow this formula, this model here. F of c plus f prime of c of x times c. Now if you notice that this first portion is simply just the tangent line equation that we saw basically from that linear approximation that we saw from the 1st degree Taylor polynomial. And then after that, then the pattern we can match a little bit better. It'll simply be the second derivative evaluated at the center C divided by 2 factorial times x minus the center C squared. So notice how there's symmetry and there's similarity between all these different parts. Second derivative, 2 factorial, and raised to the second power. So all these information will match. And the center, whatever that center is, will also be here, x minus c squared. And then likewise, the next term will be the third derivative evaluated at the center c divided by 3 factorial times x minus c to the third power. And our general rule is simply the nth derivative, whatever that nth derivative is, the 8th, the 10th, the 15th derivative, centered at c over n factorial. So if this is 15th derivative, then this will be 15 factorial x minus c to the 15th degree. And this portion simply represents coefficients, or the number attached in front of this polynomial, this degree polynomial. And this Taylor polynomial is named after Brock Taylor, English mathematician. So again, just to review here, the first degree Taylor polynomial is simply a tangent line to our function at x equals c. And this portion, again, is the coefficient of our polynomial of this x minus nth term, x minus c to the nth term. All right, if c is equal to 0, so if our center is 0, then our function, our polynomial function, or you can call this Taylor polynomial, is basically when c is equal to 0, this is called a Maclaurin series, Maclaurin polynomial, sorry. And Maclaurin polynomial is simply a Taylor polynomial that is centered at 0. So with center at 0, all these terms will just drop out, and it'll be a lot simpler formula to follow. And what we have right now, as we saw from before, that even though the 7th degree polynomial from our first example was a pretty good approximation, it still ends up being just an approximation. Okay? And the reason why is because Maclaurin polynomials, these are just going to be a finite set of terms. So when we have finite set of terms, there's only so much accuracy that we can achieve. And later on, we'll talk about how we can have infinite series, which will do a much better job of matching exact values for a certain radius, or for a certain set of values. All right, example 3. Find the Maclaurin polynomial of degree n equals 5 for our function sine of x. Then use our 5th degree polynomial to approximate the value of sine of 0.1. And we're just going to take care of this this first portion. The finding the error for our approximation, we'll save that for a later example. So first off, a Maclaurin polynomial is simply a Taylor polynomial that's centered at 0. So we know c is equal to 0. Now we're going to build our polynomial simply by following along with our formula that we see from up here. Okay? Basically, the nth derivative evaluate at the center 0 over n factorial times x to the nth degree. Now, to determine all the parts that we need for degree n equals 5, we're basically going to have to find the derivative up to the 5th derivative, or down to the 5th derivative. So here we start off with f of x equals sine of x. We find the derivative, which is cosine. Second derivative, negative sine. Third derivative, negative cosine. Fourth derivative, after the third derivative, we go back to numeric numbers to represent that. So fourth derivative is sine. Fifth derivative is cosine of x. And now we can evaluate each of these derivatives and values at 0. So f of 0 is 0, f prime of 0, cosine of 0 is 1, negative sine of 0 is 0, Negative cosine of 0 is negative 1. Sine of 0 is 0, and cosine of 0 is 1. So now we're going to create our fifth degree Maclaurin polynomial. Now the first portion is simply, again, just the tangent line equation. So our ordered pair is 0, 0, so 0 goes here, 0 goes there. Our slope is 1 times x minus 0, so here this is simply our tangent line equation. Plus, now we can move on to the pattern here. Second derivative evaluated at 0 over 2 factorial times x minus the center 0 squared. And the second derivative evaluated at 0, we can look at our these values that we created here. F double prime of 0 is simply just 0, so the 0 goes up here in front. So we finished the second derivative. Now I move on to the third degree. So third degree is just the third derivative evaluated at 0 over 3 factorial x minus 0 to the third power. And if you look at the third derivative, that's simply negative cosine of 0, which is negative 1. So we keep going. 0 over 4 factorial, and then 1 over 5 factorial, x minus 0 to the fifth. And if we clean this up, meaning that any term that has a 0 coefficient, we can just drop those out, and that just leave us with x minus x cubed over 3 factorial plus x to the fifth over 5 factorial. Now we can always use Taylor's rule. This is what we call Taylor's rule, where we're generating all the derivatives up to match the degree of polynomial that the problem is asking for. We can always generate this Taylor's rule. However, if we can recognize the pattern for this specific function, then we can use that pattern to generate subsequent terms in the polynomial. So here, if you see that this is x to the first then the pattern is x cubed over 3 factorial, we see that these are all odd degrees, so we can make a pretty good guess that the next term will be minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial. So once we see the pattern, there's no need to go back and find the 6th, 7th, 8th derivative once the pattern is found.